express a decimal number that's smaller than 0, all we have to do is take the positive value of that number, then add a minus sign in front of it. So say I want to write minus 26, all we have to do is write plus 26 and then add a minus sign in front of it, and it becomes minus 26. That's simple. But computers, calculators, or other digital devices that use binary numbers that have only 0 and 1, they can't process plus or minus signs. So we have to find a way to express negative numbers using only 0 and 1. For that we use a method called 2's complement. What 2's complement does is it expresses binary numbers in a way that is negative but uses only 1 and 0. In order to do that, well, let's show you with an example. Let's take 5, decimal number 5, and convert it into its binary value 101. Now we have to add a sign bit in front of it. So the sign bit is 0 if the number is positive and 1 if the number is negative. Since this is plus 5, we're gonna add 1 in front of it. So in order to perform 2's complement on this number, all you have to do is invert each bit. So 1 will become 0 and 0 will become 1, and then add 1 to the inverted number, which gives us this number. So in a signed number system, when in computers there's always a sign bit in front of each number. So if we consider 1 to be the sign bit here, then this number will equal minus 5 inside a computer. So why does this work? Why does this number represent minus 5 without actually having a minus sign? Or actually this number looks nothing like minus 5 if you think. It looks nothing like the plus 5 if you think about it. This is 1011, this is 0101. Like, there's no similarities at all, and there's no sign that this could become this in its minus format. So why does this work? Because because computers work, because when we use computers, they're doing everything right. They're performing every calculation right. We're playing games and music on it, and these processes take billions of calculations per second to perform. So they must be doing it right. I mean, if they are doing it wrong, nothing would work. So why does it work? Now to illustrate this, we'll take another 3-bit decimal number, which is 4, and convert it to its binary form, which is 100. Now this give it its sign bit, which is 0. Now we do what we did last time and perform the inversion. So 0 becomes 1, 1 becomes 0. But this time we're simply going to add the original number in its inverted form. This will give us, well, it's actually very easy to do, because each place has only a 0 and a 1. 0 and a 1, 1 and a 0, and a 0 and we know the sum of a 0 and a 1 is always 1. So each place will get a 1, a 1 on, a 1, and another 1. What is this? This is the largest number of the 4-bit can represent. This is the biggest 4-bit number can come up with, 1111. And now that we have this, let's think about how we can use this to find think about how we can use this to find the negative value of this number. I mean, well, let's see. Well, we have this number here and this equals 4. So if we can somehow make this equal to 0, then we could say that, hey, this plus this can be used as minus 4, since 4 plus minus 4 always equals 0, but this isn't 0, so we must add or subtract something to it, right? Now, also have to find a process that always works. I mean, it doesn't matter what number it is, it doesn't matter how many bits it uses, it has to always work. Like, just like here, I mean, if we add any inverted number to it, the original number, it will always be all ones, as many ones as the number of bits the original digit here in 4 bits had. So, okay, so how do we make this 0 in every case? Let's try adding a 1 to it. Now, since this is the largest number of 4 bits, adding a 1 to it would give us the smallest number in 5 bits, which is 1 0 0 0. Now, if we do this to a 5-bit number, say if we added 1 to 1 1 1 1 1, then we would get 1 followed by 5 zeros. So we got the zeros, but there's still a problem. There's a 1 in front of it. So how do we get rid of this? Hey, let's do this. The original number had 4 bits, including a sign bit. So, and we have 4 zeros here. What if we just say that we're gonna stop counting once we reach the number of bits that the original number had? Like, starting from LSB, if we count 1 0 2 0 3 0 4 0, hey, 4 bits, that's as many bits as the original number had. We're gonna stop counting right there and just ignore the last one and call it an overflow. Well, then this process works for this too, for the 5-bit number too, because then this 1 is a 6th bit. We can ignore it because it's an overflow. And then the result of these two operations, the inversion and the addition of 1, becomes 0 0 0 0. And this means that the sum of the original number 1000 and its inversion along with 1 is 0000 if you simply ignore the 1 at the end, which is an overflow. And that means this part, which is the same as 2's complementing something, simply should be equal to the negative value of the original number. So if the original number is 4, this has to be equal to minus 4, because it's only the sum of 4 and minus 4 can be equal to 0. You can't add another number to 4 and make it 0. The sum will never be 0. And this is why 2's complement works. We use inversion and the addition of 1 along with ignoring the most significant bit, which is always 1 bit more than the number of bits the original number had, to produce a result of all zeros. Okay, and this makes the 2's complement stand for the negative value of the original number.